Is for lesson 6.1, rate of change and slope. We are going to focus in this video on rate of change. So in this chapter, we are starting a new chapter where we're focusing only on linear functions. So every graph, every equation, every table that we're going to study in this chapter is for a straight line. So keep that in mind as we are doing these first few examples here. So rate of change is constant over a line. If a line is straight, that means that the rate of change is the same no matter where you are on the line. It describes how steep a line is. It describes which direction the line will slant, positive if it's increasing or negative if it's decreasing. And it will also describe how the y quantity changes in relation to the x quantity. To find the rate of change, you will need two ordered pairs. So whether we are looking at a graph or a table, we always need 2 points to find how steep the line between those 2 points is going to be. So let's take a look at a few examples. The way we're going to calculate the rate of change is by finding the change between the two y values of those two ordered pairs that we choose, and then dividing that by the change in the x values of the two ordered pairs that we choose. So the formula is the change in the y values divided by the change in the x values. Over here on the right, this is just a math shorthand notation. The triangle symbol in math represents the words change. So that just tells you you're finding the difference between the two y values and then dividing that by the difference between the two x values. Okay, so taking a look at this first example, we have a table of 4 values. Remember, we only need 2 ordered pairs to find our rate of change. I usually just do the first 2. You could really use any 2, but I'm going to use the first 2. The pounds represents our x values and the price represents our y values. So what we need to do is find the difference between the two y values. So $3.50 to $6.50, that is a difference of $3. So it's an increase of 3, so it's a difference of a positive 3. If it went down, then we would write negative 3. So we want the difference here, which is 3. If it's a positive 3, it's 3. If it was a negative 3, we'd write negative 3. Then we want to do the same thing on this side. The difference from a half to 1 is a positive increase of 0.5. So we have a difference of $3, so our y is dollars, and we have a difference of a half a pound. If we divide 3 divided by a half, we get $6 per 1 pound is our rate of change, $6 per pound. Now, if you look at the table, if we you notice that there is a value in here that says $1 is 1 pound is $6.50. So you might be thinking, well, then how is 1 pound $6 if the table tells us 1 pound is $6.50? What that means is that our graph does not start at 0. It starts somewhere else other than 0 on the y-axis. If it started at 0, then you would see the value 1 and 6 in the table. Also, if it started at 0, you could just divide the y by the x, and you would get the same number for every pair of ordered pairs. In this case, that doesn't happen. If I divide 350 by 0.5, I get 7. If I divide 650 by 1, I get 650. 950 divided by 1.5 gives me 6.3 repeating, and so on. So you notice that if you try doing just y divided by x, like we did with direct variation equations, you're going to get a different number. So you might actually think, well, wait a second, then this is not a straight line. Remember, if it doesn't start at 0, 0, it can still be a straight line, but we have to look at the difference between the y's and the x's rather than just dividing y by x. So this is $6 per pound. That just means that it doesn't start at the origin. It starts somewhere else on the y-axis, and we'll study that a little bit more in the next few lessons. Taking a look at our second example, here we have a graph. You can see there's 2 points on the graph. There's more, but there's 2 that are labeled. You could use any 2 points on the graph. So I'm just going to add in a couple more here. Any 2 points on this line is fine, because the line is the same steepness between any 2 points. The steepness of the line doesn't change. It just gets closer and closer to 0. We can obviously tell this line is decreasing, so your answer should be a negative answer. So if I just use the 2 ordered pairs that they have labeled for us, our original y value, we start at 1,000 and then we drop down to 0. So that's actually a change of minus 1,000, and in this case it's feet. That's the y value. So remember, for the y value, we're looking at this axis right here for our units. And then the x value, it goes from 60 seconds to 180 seconds, so that's an increase of 120 seconds. So that means as your airplane is landing, it drops 1,000 feet every 120 seconds. So if I divide that, just to simplify it and get a unit rate, that is negative 8.3 repeating feet per 1 second. So that means the plane is dropping 8.3 feet every second. Okay, take a few minutes to try these examples and choose the correct answer. For this first example, the days is our x and the money is our y. Remember, it's always x then y, and this kind of table is x then y. So any 2 points are fine. Again, I tend to use the first 2. We're just finding the difference between the y values and the difference between the x values. So from 100 to 80, that's a drop of $20, negative $20, and then that's an increase of 1 day. So this one is nice and easy because it's already in simplest form. You lose $20 per day. Of course, if you didn't choose the 2 points right next to each other, you would have to simplify. Like if you went from 100, let's say you use this first point and the last point, from 100 to 40 is a drop of $60, and from 1 day to 4 days is a change of 3 days. So negative $60 every 3 days, but that would still give you negative $20 per day. So you just want to make sure that you simplify your answer. For our second example, we are increasing each time over here on the y value by 90 gallons. And we are increasing the time each time by 10 minutes. So plus 10 minutes each time. So that is 90 gallons every 10 minutes, which is 9 gallons per minute. Take another few minutes to try to find the rate of change from these 2 graphs. For this first example, since there are 2 points labeled, those are actually the only 2, well, you could use this 1 point down here too, but since we have these here, we're going to start at, make sure you start at the point like farthest left. You read the graph from left to right. So this is increasing. So our y value is going from 10 centimeters up to 20 centimeters. So that's an increase of 10 centimeters. And our x value is going from 30 days to 50 days, so that's an increase of 20 days. So if it's 10 centimeters every 20 days, then that's a half of a centimeter per day. And for our second graph, again, you can see it's decreasing just like the airplane. This one is just temperature divided, temperature change compared to the altitude. So altitude is like as you hike up a mountain, it gets colder. If you've never done that before, the higher you go up, the colder it gets. So any of these 2 points you use is fine. I'm going to use this first one, which is 0, 16, and the second one, which is 1010. So we start at the top because we go from left to right. So we start up here. 16 to 10 is a drop of 6 degrees Celsius. And then from 0 meters to 1,000 meters is an increase of 1,000 meters. So every 1,000 meters that you hike up in altitude, you lose 6 degrees Celsius, which you could convert that to Fahrenheit is a little bit more than 6. Is about 43 degrees. So 43 degrees every 1,000 meters, that's a lot. That's a big change. So if I want to simplify this, -6 divided by 1,000 we get is negative 0.006 degrees Celsius per meter. Okay, you can actually find the rate of change from a word problem as well. You just need to figure out which information would represent our x values and which information represents the y. So you kind of have to determine independent and dependent variables yourself just from the context of the problem. So here we have Sarah was driving a car at a constant speed on the highway. She noticed that after driving for an hour, she had 12 gallons of gas left. After driving for 3 hours, she had 8 gallons of gas left. Assume that there is a linear relationship between the amount of gasoline left and the time Sarah has been driving. So we can turn this into some ordered pairs. We have 1 hour is 12 gallons remaining and 3 hours is 8 gallons remaining. Usually time is the x value, which we talked about before. So what's happening is our y value is dropping 4 gallons as our x value, the time, is increasing by 2 hours. So you're losing 4 gallons every 2 hours, or you're losing 2 gallons per hour. Okay, so just a quick recap. If a function is linear, the rate of change is constant between any and all quantities in a table or graph. We did talk about this a little bit in the last chapter, but just a quick refresher for you. If you just take a look at the table and look at the difference between the y values, so this is a drop of 3, a drop of 3, a drop of 3, a drop of 3, as long as both the y and the x change, this is an increase of 3, this is an increase of only 1, an increase of 1, an increase of 1, and an increase of 1. If all of these are the same, then it's linear. In this case, they are not all the same because this very first one is different and only on the x side, so that makes it nonlinear. We don't know what it is. It could be quadratic, it could be absolute value, we don't know, and for these purposes it doesn't matter. We just want to determine if it's linear or not. From -3 to 3, that's an increase of +6, +4, okay, so when you first look at this, you're thinking, okay, these are all over the place. But you have to check the x side also. From -1 to +2 is a change of 3, a change of 2, a change of 4, a change of 2, and a change of 1. Sorry, that's 2. And then remember, we want to look at the change in the x and the change in the y and the change in the x and divide them and see if they're all the same. So if you actually notice 6 divided by 3, 4 divided by 2, 8 divided by 4, 4 divided by 2, and 2 divided by 1 are all 2. So this is actually linear. And that would mean that the rate of change there is 2. So here's a few other examples. To go ahead and determine which of these show a linear relationship.